All right, everybody. I don't know what you're seeing on the screen. I'm seeing a student right now. Do we have audio on? Yeah. And we're going to be proceeding to our discussion for today. And here we go.
Hi, Dr. Whitaker.
Yes.
Quick question before you start. We have construction people that are about to cut the power for the house, so I'm not going to have Wi-Fi. For the questions you said you're going to do practice, are they going to be recorded too, so I can go back to them tomorrow?
Yes, after today's lecture, there'll be a tutorial to show you how to draw a Newman projection from a sawhorse conformation. And the video will be posted as segment 5 in today's lecture notes.
All right, so it's going to be posted.
Yes, it will.
All right, thanks so much. I'm sorry I'm going to have to leave because they're about to cut the power. Have a good day.
Okay, all right. So here we are, everybody. We have test 1 is approaching, and it's next Wednesday. And once again, we're going to have a tutorial after this lecture at 1:10. I sent an email. Some details about our test on Wednesday next, not this week, but next week. You're going to receive a detailed study guide with each question outlined question by question. So there's no way you do not know what's going to be on this test. You will have actual sample questions on tests that you see multiple versions of to study from. And you're going to get a problem set. This will be available on Friday, and it will be due. The due date is already posted. I do not have it at the top of my mind. Material for the test will be all of Chapter 1. In Chapter 2, everything except for petroleum distillation in Section 2.5. And Chapter 3, only 2 sections that we will be using on every exam in Organic Chemistry 1 and 2. We will be doing what's called naming of stereocenters. So we have to know what R and S means by the end of today. It'll be coming up very soon. I'm going to jump into the Chapter 3 stuff and then come back around for the Chapter 2 stuff we haven't done yet, because I want to get to the type of chair question you're going to see on your exam, and I want to do that today. And then Wednesday, we're going to finish up with redox and all loose ends that we haven't covered that are on this list up here. So we're going to proceed today with determining R and S for stereogenic centers. We don't know what a stereogenic center is, except we have a hint that we can use a short form. I guess that would be what we call a portmanteau. Took the first part of this name and the second part of this name, the whole name, call it stereocenters. And what is a stereogenic center? This is a very good question. The relevance of it is illustrated with something as simple as your hands. Your hands, although they have the same parts in the same order, thumb, index finger, middle finger, ring finger, pinky, they're clearly different objects. So they need different names. In biology, we have the names right hand and left hand. In stereochemistry, when we have a stereocenter, we don't use right and left, we use R and S. So before we see a stereocenter, or do stereocenters, we have a stereocenter example. I'm stealing this right from the book. These carbons labeled with an asterisk are both stereogenic centers, or you can call them stereocenters. What makes them so is they have 4 different substituents on them. So there's a lot of carbons here, but only this carbon in this molecule and this carbon in this molecule are stereocenters. Here are the 4 groups. We have a hydrogen, a chlorine, a methyl, and a propyl. They have different names. They're different groups. Okay, same for this carbon here. Same 4 groups. So these are mirror images of each other. In fact, I drew an imaginary mirror here, and sticking close to the mirror is the methyl, and straight up is the propyl, and going away from the mirror and to the left and down is the H, and away from the mirror to the right and down is the H, and away from the mirror and with a wedge is a chlorine, and all of that. Now, this carbon here is not a stereocenter. It has 3 identical hydrogens, so it does not have 4 different groups. Same story here, except it's got 2 hydrogens, a CH2 and a CH3. 2 hydrogens, that's not 2 different hydrogens, they're the same, so not a stereocenter. Okay, so let's follow the rules for naming a stereocenter as R or S. Step 1 is the easy part. Identify the stereocenter. That's when I put the asterisk there. This is 2 separate problems, by the way, for this same molecule. Back last week, we learned how to name these things. Does the name 2-chloropentane make sense with what we learned last week? I sure hope so. It is a 5-carbon chain. The longest chain starts here, 1, 2, 3, 4, 5. Pentane off the second carbon is a chloro group. So we have 2 molecules that right now have the same name, but clearly they're not identical to each other, just like our hands. So we're going to be adding to those names in front. Now we have to prioritize the 4 different groups on the stereocenter, and it's these gentlemen here that came up with the system, and we have to live with the system. We can't invent our own system for naming stereocenters. So read this very carefully. Priority 1 goes to the atom. Notice I did not use the word group there. The word group there will get you in trouble if that's what's in your mind. Atom. The heaviest atom is a chlorine, which weighs 35.45 grams per mole, straight off the periodic table provided to you on every test. Okay, and the lightest atom, the number 4 priority, will go to the hydrogen with a weight of 1.0079 grams per mole. So that immediately establishes priority number 1 and priority number 4. Why didn't I do 2 and 3? Because following the rules here, we have a carbon atom and another carbon atom. That's a tie. We have to talk about what to do in the event of a tie. Some of you have already jumped to a conclusion, haven't you? You say, oh, I'm going to pick this one over this one because it's a bigger group, and you use the group word, you will be doomed in the future. When I pick a smaller group up there to have a higher priority. It's going to happen very soon. So what do you do if there's a tie? That's a good question. If there's a tie, then you need to compare the mass of the heaviest atom attached going outwards from the stereocenter. So we've established we have a tie between these 2 carbons. Question 1, what is the heaviest atom attached to this carbon? Another carbon. Please don't go back to the stereocenter ever. You're always moving outwards 1 atom. Atom is the word at a time. Heaviest atom attached to this carbon is a carbon. Heaviest atom on this carbon moving away from the stereocenter is a hydrogen. I have circled them here. Compare these 2 atoms now. The only reason we're comparing these 2 is because there was a tie earlier on. Carbon 12.01, hydrogen 1.008. Carbon's heavier than hydrogen. That's why we have a 2 up here and a 3 here. And now what we have is rule 3. We're supposed to reorient the molecule so that the number 4 group is behind the page on a dash. In our first examples, I will have done that for you already. If you are into statistics, you will have the number 4 group on a dash 25% of the time, because we have 4 bonds and only one of them is a dash if you draw your tetrahedron properly like this. Okay, we will teach you what to do if the number 4 group is on any of the other positions. Right now it's the hydrogen and it's on a dash already. We will learn tricks that let us do reorientation without rotating molecules in our mind. I'd like to point out that's a skill I don't have, to be able to do that inside my mind. If you can do that skill, you might want to consider a career in dentistry where you're putting mirrors in people's mouths and still keeping track of which group is to your left and right. I can't do it. But I have a trick that even somebody who's spatially challenged like myself can reorient the molecule without visually doing it inside their head. It's called the double switch method. It's coming up a little bit later. So let's talk about what we have so far. We have this situation where we have a carbon, and we just need the numbers right now. And the numbers are 4 for the hydrogen. Well, that is very large. I remember why now. I'm setting up some stuff ahead of time. There we go. The 4 was here. I like circling these numbers so I don't confuse them with chain numbers. The number 1 was the chlorine. I'm looking up at this molecule here in case you're concerned. I will put the numbers here. After we broke the tie, we had 1, 2, and 4, and 2 and 3 circled here already. So after you followed those steps and got 1, 2, 3, 4, the only question in step 4 you need to answer, and I'm not going to grab it from the book, it's very simple. 4. Connect 1 to 2 to 3 with a curved arrow. If your arrow is clockwise, we call that an R stereocenter. Counterclockwise equals S. I'll briefly mention the origin of those names, and they should be apparently can't do it that way. It should be italicized. I'll make it bigger and move it. And we'll make it bold. 28's nice. We'll move it. Okay, you ready to do that? Let's go with that one. And we got our 1, 2, 3, 4. You're going to connect 1 to 2 to 3. And the reason why we have step 3 to reorient the molecule so that the number 4 group is behind the page is to convert a 3-dimensional problem to a 2-dimensional problem. After you've done step 3, which was done for you already, you can ignore the number 4 group. It's now a 2-dimensional problem. And we are going to connect 1, 2, and 3 and ask ourselves, there's an arrow connecting 1, 2, and 3, like it says, connect 1 to 2 to 3 with a curved arrow. And if you're like me and you just do that and you stop, there's a chance I'm going to think that's counterclockwise unless I keep the circle going around and around and around as I'm doing it. Well, for you, I should be doing it this way because I'm on this side, you're on that side. But anyway, everybody's on the same side now. I keep it going around in a full circle until I realize that's how a normal clock goes, right? That's the one with the hands on it. I know not everybody gets training in those nowadays, but that's clockwise direction. And we call that R, and it comes from a Latin word called rectus, means righteous. If it was counterclockwise, it would have been in the opposite direction, and it's from the Latin word sinistris, S, would be counterclockwise. So the full name of my molecule, keeping in mind, no, we don't have the name on this page. We have it on the previous page. R2-chloropentane. Why don't we steal the whole thing? Here we go. No, I'm mixing my 2 programs up. Here we go. I'm gonna steal this. I guess I didn't need the title. Over here. And what we got here is, that's the first molecule, and now we know more information. Its full name would be R2-chloropentane. And with our information that we just learned, this came out to be 2, and this 3. And in this one, this is 3, same. And this is 4, and that's 2. And you shouldn't be surprised. The first one is our first example, and it is definitely clockwise. The second one, 1, 2, 3. 1, 2, 3. Connect 1 to 2 to 3. Ignore 4. Definitely counterclockwise. What goes in front of that name? Hit pause. What are you going to put there? You're going to put an S there. Okay, if it lets you. Pen's off. There we go. So now they have 2 different names. Why? Because they're 2 different molecules. Why is this important? Handed molecules behave differently. Oh yeah. Chapter 3. There's a lot of vocabulary in chapter 3. You will not be responsible for any of the vocabulary except for 3 things that we've already looked at today. The word stereocenter, the letter R, the letter S. So if you see other words like enantiomers and diastereomers and chirality, those are for next test, okay? We're not skipping those sections. I just want to get to this because it belongs with your introduction to nomenclature. They need to be together. Okay? So R, S, stereocenters, that's all you need from chapter 3. Okay, we'll do another example before we move on to this double switch method. We often have molecules. A new page is in order here. We often have molecules with more than one stereocenter. It's very common. And let's do something like this. That's supposed to be a dash. It's pretty lame. And up here, we'll go like this. And over here, we'll throw a halogen here. And we'll throw, I don't know, hydrogen there. 2 stereocenters, 2 separate problems. We'll deal with them separately. Stereocenter 1 in blue. Stereocenter 2 in black. And we'll deal with stereocenter 1 on the left and stereocenter 1 on the right. 2 separate problems. Okay. Oh, wow. I jumped right to a stereocenter that has nothing but carbons attached. This is a 4-way tie. So I can't even do 1 and 4 right from the start. Do not panic. I'm going to copy the tetrahedron as I see it and just keep going 1 atom at a time. And the heaviest thing on this carbon, which is right here, is another carbon. The heaviest thing on this carbon here is another carbon, 1 atom at a time. The heaviest thing on this carbon, remember, you got to move away from the stereocenter. Don't come back. The heaviest thing on that carbon is a hydrogen. And the heaviest thing on this carbon is another carbon. So we are comparing these things highlighted in pink because they are the same distance from the stereocenter. And I think the only piece of information I have now is which of those carbons will have the lowest priority. Which one is it? It's the one with the lightest atom as, this is going to be weird, the lightest atom as its heaviest atom attached. I put always heaviest atom, heaviest atom, heaviest atom, heaviest atom. Which of those four is the lightest? And that will give us our 4. We're done with this carbon. This group is over. We still have a tie. We have a tie here, here, and here. Go back to the same carbons we were comparing and ask the same question again, except don't use the pink. Ask this question. What is the next heaviest atom attached to this carbon? And we'll put it in a different color highlighter. It's another carbon. And we'll do that in baby blue. We're comparing that carbon. And what's the next heaviest atom attached to the carbon here? That's this carbon here. You can't tell me there's another carbon. That would be a lie. So we're going to be comparing this blue carbon to a hydrogen. Blue. So I know right away, this carbon up here, the second carbon here beats this hydrogen. And I think I have the same story down here. We have another hydrogen. We have highlighter blue. So right now, I think I've established priority number 1. Compare the blue highlighters. We did pink first. Then we went back and had to do this second. Could have got away with that, but we did this second. And that gave us our number 1 of all the blue highlighters. Carbon has the highest mass. Now, I could just carry on forever here. To break the tie between 2 and 3 or 3 and 2, we don't know which one yet. You got to finish off that first carbon. And I mean, they're the same. So what do you do when you're finished with those 2 carbons? They're still tied. They got exactly the same things. Well, you go to this carbon, which is this one, and ask yourself, what's the heaviest thing on there? It's a C. What's the heaviest thing on the second carbon away from the stereocenter here? It's another, let's see. No, there's the first. And here's the second. There, 1 and 2. It's got another carbon. And they both have H's. They're going to be, I had to circle around. I'm going to go with a different highlighter because now we're comparing these carbons in purple. And they're still tied, right? I'm not highlighting this and this. They tied. And I'm not going to highlight these and this and this. They tied. And these tied, but they're highlighted because I'm going to compare the heaviest thing off this carbon. And some of you have already anticipated. We finally have a number 3 and a number, what's the heaviest thing here? Yet another carbon. And that'll be one more color highlighter here. My apologies, I jumped to an example. I should have done the N stereocenter before this one. This one's got more going on. All right, so we had a dead tie all the way until we got to purple. CH2, CH2, C, CH2, CH2, C. Now you got to compare the purples. Which one has the heaviest atom going outwards? H loses, C wins. We finally have a number 2 and a number 3. And that's not what I want to do. Red 2. Notice I put the numbers on the atom attached to the stereocenter. Always, please. And the 3 is over here because yellow H lost to yellow carbon. And if you do your connection now, you have a stereocenter that's clearly clockwise, and that would be R. And there you have it. That was a lot of work. You do get better at this, but there's only one way, and you know the way. Practice. There's lots of practice items at the textbook. Moodle makes you practice a whole lot. And now we're going to move over here and do the easier stereocenter. Once again, I think we should have started here. This is very much like our first one, isn't it? We can immediately do the 1 for fluorine. It weighs 19 grams per mole. It's heavier than any carbon. And we got the 4 for an H, weighs 1.008. We got a tie. I don't think we have to do as much elaborate highlighting as before, do we? Our first highlighter we had was pink. We have a tie here and here. And I think we break the tie as soon as we compare. Next was the blue. Yeah. This C is the same distance away from this H, which I haven't drawn yet. Oh, still haven't drawn. Comparing that, heaviest atom on this carbon away from the stereocenter, H. Heaviest atom on this carbon away from the stereocenter, C. So we have a 2 for a carbon beating an H, and a 3 for the carbon with the H. And this stereocenter is sinistrous. It's very much like our first example. And that's S. Now we're going to name our whole molecule. I wonder if it'll let me do it down here. That should do it. Let's give the whole name down here. We had an S for our new stereocenter on the right. And we had an R for the other stereocenter. S here, R here. Now the numbering for the longest chain, let's do it in a different color. You should number from the right to put your lowest number for your group on 2, 3, 4, 5, 6, 7, 8, 9. Let's verify that. That's a 6. It doesn't look like a 6. 1, 2, 3, 4, 5, 6, 7, 8, 9. It's a nonene. The 3 groups. Sorry, there's 3. There's a methyl. There's a fluoro. And this V has an iso in its name. Iso with 3 carbons. Isopropyl. FGHI. F before I for isopropyl. Before M. So 2 fluoro. Isopropyl's on, I didn't copy the number. Oh, it's a 6. I can't read it. 6 isopropyl. And 6 also has a methyl. You write that down as a nomenclature answer, you have 1.5 out of 3 points. Whoa, what's going on with that? Why didn't I get full credit? I named it perfectly. Well, you only named one of the isomers. Here, I'm going to give you your grade over here. 1.5 out of 3. Your name has to indicate the stereocenter on carbon 2 is an S stereocenter. 2 is an S stereocenter. Stereocenter on 6 is R. And that's how you get 3 out of 3. That's how important stereocenters are. They're worth half the credit in this question. Typical policy for this course and this instructor is 0.75 points for each stereocenter. So do the work and get your full points. There are 3 other isomers for this molecule. I can quickly give you their names. One isomer would be 2R6R, and a third isomer would be 2R6S, and a fourth isomer would be 2S6S. That's all the combinations of R and S when you have 2 stereocenters. Please don't worry about what I just said. That's going to be in our introduction to drawing those isomers that you don't have to know the names of on test 1. Today's all about doing R and S on stereocenters. So here's the deal. We have to do a stereocenter where the number 4 group's not already on a dash. And how do we do that? Apparently there's a trick we have to learn first. And here it is, the double switch method. It says it's found in a few pages. That's not very precise. It's found in section 2.5. Let's go find it, shall we? Here's the book. Okay, it's not moving for me. Why are you not moving? Here we go. A lot of stuff. I said 2.5, didn't I? 3.5. The double switch method. I want to point out this is not chemistry. This is a trick that gives us the right answer every time. And when we're talking nomenclature, all you care about is the right answer. So it's a trick. It's not a thing. It's not what's happening in chemistry. It's a trick that lets people that have minds that can only think in 2 dimensions come up with an answer that's a 3-dimensional answer. And let's just look at this and see what's going on here so we can try our own practice examples after this one. So we're supposed to do the normal steps of assigning priorities on the stereocenter. And then this method is needed if the number 4 group is not on a dashed bond. That's one that's behind the page if you forgot. You should do a double switch to get it there. Okay, so we're going to do the double switch and then connect our 1 and 2 and 3. So when we do the 1, 2, 3, 4, I'm going to skip to the numbers right now. Step 1, assign priorities. You got an O for 1. You got an H for 4. Notice I'm only talking about the O and the H. These are atoms attached. We had a tie with the carbons attached. The heaviest thing on this carbon was a C. The heaviest thing on this carbon was an H. That's why this is a 2 and a 3. This is just what we did previously. Now, when you do your answer, you don't have to do it this way. In fact, I'm going to steal this. And where is it? Here we go. You don't have to redraw the molecule. That would be very time consuming. Let's minimize. This is section 2.5. It's called the double switch. Okay, after I do step 1, here's what I do. we're supposed to copy the tetrahedron. So I'll put it underneath because it's a lot simpler to do it this way than right above it. Notice I'm not moving any bonds. That's the beauty of this method. You don't have to rotate things in your mind. I don't need the groups, I need their numbers. Now, if you just did a single switch on any of the two groups and then connected 1, 2, and 3, I promise you get the wrong answer. That's what a single switch does. It converts a stereocenter that used to be R to one that's S. Or it converts a stereocenter that used to be S into one that's R. That's what single switches do. I could prove it with toys. I don't have toys. You got to believe me. It's true. So if you keep in mind that one fact that a single switch changes your stereocenter, then realize a second switch must get you back to the original stereocenter. Every time you do a single switch, you go to the other stereocenter. There's only two types, R and S. So if you did one switch of two groups, that's called a single switch. You go from R to S. And now you pick any other two groups in the molecule and switch those. You're back to the original R. Fair enough? So why do we always find the 4 group first and then switch it with what's on the dash? Because that's what the textbook says to do. Well, the objective of the double switch is to get the number 4 group on the dash. So find the 4 and put the 4 on the dash. I don't care what's on the dash. Find the 4, put it on the dash. I only need the number. I don't need you to copy the group out. That's a waste of time. You switched it with, in this example, the 1 was on the dash. It could have been a 2. It could have been a 3. In this example, it was a 1. That's a single switch. Don't stop. To finish the double switch, you've got to switch the other 2. That means your 3 and 2 switch. So 3 will be on the wedge now, and 2. And I promise you, you really haven't changed this molecule at all. It's the exact same molecule redrawn, and it has the number 4 group on a dash. You are now permitted to connect 1 to 2 to 3 to get the right answer. Keep it going round and round. For you, it's going to look like this. It's going to look like that. And I'll just do it. It looks like that for you right now. That's R. This is an R stereocenter, which means this was an R stereocenter. The double switch does not change the stereocenter. It gives us the answer. It's good. Let's do another one. Double switch. Let's talk about a molecule like this. And I want the whole name of this molecule. Those don't have to be chlorines. Let's make bromines, and let's put 2 of them. Sometimes you think I'm trying to trick you, right? You're saying, wow, why has he got 2 stereocenters again? Well, he doesn't. Is this a stereocenter down here? No. Stereocenter has to have 4 different groups. So the only stereocenter in this example I care about. Well, there is only one stereocenter in this, so it's there. We have to name it. Let's do all this. Oh, got a little too much there. Nice. Whoa. A little far down. So we got to do our 1, 2, 3, 4 deal. Oh, I want to make it a better example. Not hard. Always thinking, what can make it a little better? If I change that to an I, do you think it changed anything? The answer is no. Number 1, which atom of the 4 that I'm about to list is the heaviest atom? Chlorine, 35.45. A carbon, 12, 12, 12. We got 3 carbons. Notice I did not get to the iodine before I decided that number 1 was chlorine. Now I've got a 3-way tie for number 2. Carbon, carbon, carbon. Which of those 3 carbons has the heaviest atom attached? Weighing in 127 grams per mole, an iodine is much heavier than a carbon. Notice this carbon here is the same distance from the stereocenter as this iodine. And this carbon here is the same distance from the stereocenter as the iodine. So carbon with iodine is going to be 2. So my highlighted portions here are tied. Once again, we're just getting to the point where we can do a double switch. These 2 are tied, and they both have 2 H's and a C. Well, the H's are not worth talking about. We go to the heaviest atom, and then they're still tied. They're still C. But what's the heaviest thing on this C? A carbon. Same distance away. What's the heaviest thing on this C? Don't say this carbon. No, there's bromines. So which purple highlighted atom has a higher priority? And it's the bromine. That went really fast. So what you want to do before you come back to this segment of the video is have practiced about 20 R and S determinations of groups 1, 2, 3, 4 before you look at this, because that was like our 20-minute lecture in 2 seconds. But now we can practice our double switch. We don't have the 4 on a dash. Double switch is necessary. You've done the priorities. Part 1 is to redraw the tetrahedron. Don't move any bonds. And that dash looks like it's pretty much straight across. Find the number 4 group and put it on the dash. Ask yourself, hey, what used to be on the dash? Because it had to switch with 4. It was a 2. I told you, it doesn't matter what the number is of the thing on the dash, you're switching it with the 4. That's a single switch. Please don't leave this as 1 and this is 3. You'll get the wrong answer, and all this work is a waste of time. So once you've done a single switch of the 4 with whatever was on the dash, do a switch of the other 2. And now you see that this one is an R stereocenter. Here's the connection. 1, 2, 3. You can ignore the 4 because it's on a dash. That's the system, guys. Don't try to find logic in the system. It's the logic of the people that decided. It's like the same as the people decided we're going to call this one right hand and this one left hand. We've lived with it forever since then. So we got R, and we need the full name of my molecule. And it's got a lot of good stuff. I wonder if I still have it in memory. Yeah, I do. Ooh, tricky. There we go. Now this is a molecule that's got, no matter which direction you number it, it goes 1, 2, 3 if you go this way, 1, 2, 3. That way has 2 groups on 1 and 2 groups on 3. If you go the other way, it's the same story. And remember, I told you, I do not enforce the U-Pack rule that goes one step further that can actually break, that actually says the green is better than the black, and I'm not going to tell you why. I'll just go with the black here just to show you that rule I don't enforce. If I use the black numbering system, I have 3,3 dibromo, leave room in front. Why is bromo first? Bromo starts with B. Chloro is next, begins with the letter C. It's on 1. Carbon 3, 1 also, sorry, 1 has a 1 carbon group. 1 carbon groups attached to a chain are always called methyl, but the group has a group on it. It's a fluoro. So please get this straight. You got to name the chain attached to the ring, in this case ring, or name a group attached to a chain. You got to name the group at the end. Methyl. And what's the group on the methyl? It goes ahead. It's a fluoromethyl. And this is the systematic group naming. Normally require, okay, it normally requires parentheses to say where the fluoro is attached to the methyl. Think for yourself for a few seconds. Why can we omit the print? I'm going to draw them for a few seconds and then I'm going to erase them. Why is it not necessary to do that and say 1 fluoromethyl? The reason is there's only 1 carbon in a methyl. You don't need the parentheses, you don't need the 1. And what kind of ring is it that it's attached to? You guessed it, cyclohexane. Yeah, it's a long segment, this one, isn't it? Wow, 45 minutes. Let's finish this segment. We determined with our double switch method that it is an R stereocenter. There's your full name. And sadly, this one's only worth 2 points. 2 out of 2. If you omitted the stereocenter, it would be 1.25 out of 2. We're going to come back and do an example with a chair. And we're going to integrate this stuff into it. And we'll be back soon. And see you in 5.